we will be looking at the running time analysis that was discussed this week. So we'll start with the linear search and binary search, and then do some more discussion around the running time analysis. So actually, yeah, let me just reuse this code. So you might have already seen this in the class. So this is a linear search code. So basically, you're given an array and you are given what you want to search in that array. So the way the linear search works, it just loops over the array entirely, and if it finds the search element, then it returns the index. Otherwise, let's say it returns -1 to indicate that it didn't find what we were looking for. So anyone can tell me what is the time complexity of this?
Sir, like since we are doing size number of iterations, so it should be something like size.
Right. So we are doing. So the way it was described in the class was basically we can count the number of operations that this code will do in the worst case. So in the worst case, what will happen is it will go over the entire array and it will not find anything and return -1, right? So going over the entire array will go over it size number of times, and within every loop iteration we'll just do a constant number of operations. So we are doing one comparison check, one increment, one equality check. So we are just doing constant number of operations. So that's why the overall time complexity, we call it order of size. So a better way to do search is if our array is sorted, then what we can do is we can start with two pointers, start and the end, right? End is size -1, start is 0. And we can say while end is greater than equal to start, I'll take the mid. So mid is basically the middle of the array. And then I'll check if search is equal to mid. If so, I'll return mid. Otherwise, if the search is greater than mid, so I will move start here. So now array searching. If search is less than mid, then I have to search in this array. So in every loop iteration of this while, we are breaking down the original array into half. So previously we had size number of elements. Then the next time we'll have roughly size by 2 elements. Then next time we'll have size by 4 and so on, right? Um, so I think this was also discussed in the class. So what is the time complexity of this?
Sir, log n of base 2.
Right. And can you explain why?
Sir, in the first step, sir, it is we are dealing with a size array of size n. In the next step, we're dealing with n by 2, and this will go on up until the size of the array becomes 0. So
Right.
we calculate that how many times this is going to happen, so that we get log n base 2.
Right. So number of loop iterations is basically, if we assume, let's say if we call it L, so 2 to the power L is basically size. Because every time we are cutting down the array by 2, so that gives us L as log base 2 size. Okay. Is this clear? Are there any doubts here? Like what is binary search and why it works? Okay. So the other way to write the same thing is using recursion. So this one is using loop, right? So the same code can be written using recursion in a much cleaner way. So what this is saying is I'll take the array, I'll take the search element, and I'll also take the start and the end. And if end is less than start, then I'll say, okay, return -1. So this is similar to breaking out of this while loop, right? We break out of the while loop when end is less than start and we return -1. Or we can do long mid is end plus start by 2. If search is equal to a mid, we return a mid. Otherwise, we'll return the right half of the array. And if the search is less than a mid, we return the left half of the array. So I hope this is clear to you. So next what we can do is we can run this program and plot the running time. So um, let's start with some smaller numbers.
Sir, just a small request, sir. Can you please increase the font size? It is a bit difficult to see. Thank you, sir.
Sure. So yeah, we'll run this program. So basically what I've done is we'll create an array, and since we want it to be sorted, we will fill 0 to size into the array. So this array will be sorted, and we are searching for the last element. So we will not find this element, right? Because I is never equal to size. And then, so this is kind of like a worst case runtime. And then we'll do a linear search, and we will calculate the time it takes to run linear search. Then we'll run binary search and print out the time it takes to run binary search. So let's run this. Okay, so it says for 1000 elements, and then we have to print the elements. Okay, so for 1000 elements, binary search and linear search takes a bit higher time than binary search, but not by a lot. So let's try to increase the size of the array. So I make it to 10,000. Okay, so now, so previously it was taking around 2.5 times. Now it is taking around 10 times. And the binary search is taking roughly the same amount of time. So actually this is not proper. We should run every experiment 5 times to remove like some noise, but we are just going to be a bit crude here. So when I run it with 10,000 elements, the binary search is taking a similar amount of time, but now it is taking 100 times less. So basically you can roughly see the growth of linear search, right? So when I increase the elements by 10 times, the time is increased by 10 times. So let's keep doing this. Right, so it's shifted by another decimal point here, and this has gone up a little bit. 0, 0. Okay, so now this is giving me a segmentation fault. So basically what happened is it is trying to allocate an array with 1, 2, 3, 4, 5, 6, 10 million entries. So 1 crore entries inside the stack. So actually your stack, I think we discussed at some point, your stack has limited amount of space. So when we are trying to do this int a size, basically this is crashing because the stack doesn't have that much space. So there is a way to get around it, which is so by making it a global variable, we are saying we are not putting this a on stack. We are putting it in a different space for global data. So let's see if this works. Yeah, so this is now not giving segmentation fault. So this is just a side note, right? Like yes. So again, we can see this is the running time is again multiplied by 10 as expected. So we do it again. And now we can start seeing the program is starting to get a little slow. So it's taking 0.2 seconds. If I multiply it by further. Yeah, so now we can feel the program getting even slower, right? So, so basically linear search is growing by factors of 10 every time I'm increasing the number of elements by factor of 10. So this is making sense because we said the linear search is order of n, right? So roughly we can see the running time is increasing by factor of n, but binary search is O of log n. So log n is actually very, very, very small than n. So I hope you can appreciate like this algorithm is much more efficient than than linear search algorithm. Cool. So any thoughts, comments, questions so far?
Sir, every time we increase the input size by adding one zero, so multiply with tens, and why is it not that exactly the time linear search is also getting multiplied by 10? It is a little bit off.
Yeah.
That also. Yes, sir.
Yeah, so that is a very good question. So actually that gets inside how a computer works. So this laptop right now is not only doing this computation, right? It is serving serving my video to the Teams channel. It is serving the screen. So basically, the computer is being pushed for resources um, from many different running programs concurrently. Like I have a lot of running programs. So depending on, so basically what computer tries to do is it tries to give a fair number of slots to every running program. And this is like, again, advanced. You learn these things in OS, these things in OS, operating systems course. So basically, because there are a lot of concurrently running programs, the amount of time your program got can vary. So even if I run it again, let's say I run it again without changing the input, right? So it will not take the same amount of time actually. So let's see. Right. So the amount of time is slightly different, 2.42, 2.52. And if I run it again, this time will again be different. So basically, there are a lot of random events going on in the computer right now while we are running the program. So the next question is, okay, if this was the only program running on the system, will we see the same time? So that is that is going to be more true. Like you will see less amount of variation, but you might still see variation. Um, because the operating system is doing just a whole bunch of things underneath the program. So yeah, but for the scope of this class, like roughly the amount of time stays the same, but you will never see the same exact same time. So that is why it is best. So if we are doing this analysis, it is best to run it like 5 times, then plot a mean and standard deviation. Yeah. Okay. Any other question, thoughts? So another thing is, interestingly, we were actually calling the binary search. This was the recursive program. So interestingly, actually, the if you think about it, we went into a very deep recursion, right? So when we have this is I think 100 million. So when we have 100 million, 3, 4, 5, 6, 7, 8, 9, this is like 1 billion. So when we have 1 billion entries, we will go into log billion. Actually, yeah, that's not much. 10 to the power 9. Yeah, that's like 27. Okay, never mind. Yeah, but basically the point I was trying to make is this we discussed in the previous help session that this is a tail recursive program. So basically when you are doing this recursion, this is not building up the stack. This is just going to reuse the same activation record when calling when making a recursive call. So that is why you can actually scale this program to on larger and larger inputs without running out of stack space. Okay, great. Cool. Um, so yeah, like I think now we can get into some meta level discussion. So basically, I don't need to share my screen for this. Some comment. Okay, cool. Yeah, so so I want you to appreciate the beauty of running time. So let's think about, let's do a little bit of role play. Let's say we are all algorithms researcher here, and we are all coming up with new algorithms, right? Um, so I'll just pick some names. So uh, let's say Ananya in class came up with an algorithm saying, okay, this is a problem, let's say a search problem, and this is my algorithm. And I claim that this is a great algorithm because when you run it on these inputs, it takes this much amount of time. Okay, so everyone is intrigued, like that is a bold claim. And this is an important problem that Ananya has solved. So let's say Ravi is um, motivated to challenge what Ananya has done. So Ravi comes up with a new algorithm, right? And Ravi says, okay, so I have a new algorithm for the same problem, and now I claim that my algorithm runs better than Ananya's algorithm because when I run it on my laptop, it takes, let's say, 20% less amount of time. So do we believe this, right? Can we claim that because Ravi has run the same problem on a different input on his laptop, is it really a better algorithm than Ananya's? So any thoughts like what can go wrong in this kind of claims?
Sir, we should run both of the algorithm on the same computer.
Right. So that is a big problem, right? So currently we are in the call 100 class. So we are all colleagues and we are in the same timeline. But let's say Ananya had given that algorithm in 1950s, right? When she was running it on IBM, like a very old machine, right? And now basically Ravi is stuck. So he cannot claim anything because he doesn't have access to that machine. So is there another, what else can we do? Like, let's say the original machine is unavailable, right?
You can check the time complexity of the program.
Yeah. So another approach is basically Ananya has, let's say, released inputs and also a program, right? Like this is my program, these are my inputs. So even though you don't have the same machine as me, whatever machine you have, you can try to run this program on that input and you can try to improve my program. If you can do it, then you likely have a better algorithm. So that is a bit of a better approach, right? Like now we are comparing apples to apples. So we are running it on the same machine. Um, but is there some, so we are going to build up to time complexity. So, but is there something else that can go wrong? So basically, it's running on the same machine. Ananya has written, given their original code, and the V has written a new code. So, is there something that can go wrong in doing such comparisons?
If you're using different inputs, they might change the time that it takes.
Right. So maybe they're using different inputs. Okay. So okay, we can de-risk it by saying, okay, I'll use the same inputs for the two programs.
Sir, even then, it might happen that the uh, original algorithm was optimized for a different machine and the newer one. So, because the system has changed.
Exactly. Yeah, that is a very nice response. So basically, the system characteristics have changed significantly from 1950 to 2020, right? Like your CPU can run much faster. So previously, your computer used to be what is called memory constrained. So you didn't have a lot of RAM to play with. So you only had, let's say, a few KBs of RAM. So maybe Ananya's program was doing some kind of basically trying to get around that issue by moving things from RAM to disk and then from disk to RAM and some such things, which are no longer required on new machine, right? So maybe Ravi has written a smart program, a program that is much better suited for his machine, but that doesn't discount what Ananya has done, right? Like maybe that doesn't really prove that Ravi has built a better algorithm. So what else can go wrong? Okay, let's say, so okay, let's bring them both to the same era. So we are both in the same era. One and they are running the same program on similar machine. Like they are running two programs on similar machine. So what else can go wrong?
Sir, even now, like even if they are running on the same machine, we still don't know what will happen for every possible input. Because even if they're running the same inputs, one algorithm might fail for some other input.
Nice. Yep, that is a beautiful
Yeah,
response.
the worst case inputs might be different for both programs.
Yeah. So basically, maybe what Ravi did is a bit of a cheating, right? So maybe he optimized his program for that particular input, right? So say let me share my screen again. So let's say I write a, so I know what is the input that is that we are testing here, right? So I claim, so I about oh, no. Okay. Uh, so let's say I know that the input is we are always searching for things that are right. So this is my new algorithm for search, right? So this search, what it does is it just returns -1. So for the particular input that we are testing this program on, right? This input it does give the correct output, right? And it is much faster than binary search. But of course, this is really incorrect. First of all, it is incorrect. It doesn't work on all the inputs. Um, and secondly, other way to say it is it is optimized for just the benchmark. So let's say so basically Ravi knew the benchmark he has to compare on with Ananya. So he can just go ahead and optimize the program just for that benchmark, right? He doesn't have to handle every side case, maybe the worst case analysis, if you run it on input outside of that benchmark, it is really, really slow. But if you run it on the benchmark, then it is a very fast program, right? So that is another kind of thing that can go wrong. So anything else? What else can go wrong? So another thing that can go wrong is basically different languages have different speeds. So maybe let's say Ananya's program was written in Java, and we know like C is much faster than Java. So maybe Ravi just wrote his program, which is identical to Ananya's, but it is written in C. And then he's claiming I have a better algorithm, right? So again, that would be cheating because it's not really the algorithm, it is the language runtime itself. So basically, this is the problem we want to solve for all of us. Like we are all algorithm researchers here. So we don't want people to cheat each other, right? So we don't want people to like depend on a particular architecture, depend on a particular language runtime, depend on a particular implementation. So the way to de-risk all of it is I'll just compare worst case, right? So I don't want you to cheat on a particular benchmark. So if you can do well on the worst case, on if Ravi's algorithm is really doing well on the worst case compared to Ananya's algorithm, then we can claim that Ravi's algorithm is actually better, right? And the thing we want to do is we don't even want to run the program. So we just want to count the number of instructions and and just say roughly how many number of instructions are there, right? So we don't really care about so maybe a new machine has a particular instruction for compare that does compare and add in the same instruction. An older machine compare was a different operation, add was a different operation. So we don't want to get into these kind of details while comparing algorithms. So that is why this actually the running time is actually very, very beautiful. Like you can look at programs, algorithms proposed in 1950s, and you can compare your own algorithm with that. So that is actually very, very powerful thing. Yeah. So any thoughts on that? Like, I hope you appreciate the beauty of this. Like without running time analysis, the field of algorithms might have looked very different and very cumbersome, actually. Okay, great. So the second point is around this atomic instructions. So the second point is basically we are counting the number of operations we are doing in a program, right? So we assume that less than takes one constant amount of time. We assume that plus takes constant amount of time, right? So that is why, so that has not changed in the past um, from the start of computing, right? So what took constant amount of time still takes constant amount of time. So there are always optimizations in architecture, but we don't consider them much. But basically, if you have different kind of these basic operations, then your algorithmic analysis might look very different, right? So we can kind of brainstorm an idea here. So let's say this is a puzzle, and you might have seen such puzzles. So this is a puzzle, right? So there are 12 identical looking coins. One of these coins is counterfeit and is known to be lighter than the genuine coins. What is the minimum number of weighings needed to identify the fake coin with a two-pan balance scale without weights? right? So basically, we have 12 coins. One of the coins is lighter than all the other coins, and we want to find out the least number of weighings we can do to identify the fake coin. So now this is not really a computing problem, right? Uh, you are working. So basically, you are working with your hands, right? And you are working with a two-pan balance scale, right? So you are not really working with a computer here. But I would argue that this is still a algorithm problem with different set of operations, right? So basically, what does your two-pan balance scale give? So your balance scale basically says that if you put some amount of weight here and some amount of weight here, finding which one is heavier is a constant time operation, right? So that is the basic operation that this weighing machine supports, right? And basically, we are being asked to design an algorithm so that we can minimize this number of weighings that we make. So this is very similar to an algorithmic problem, but just that the basic operation is different. So the reason I emphasize is basically algorithms is a topic beyond computer science, beyond computers, right? So you can, if you are really creative, you can think about algorithms in the physical world as well, where you just need to think about what are the basic operations and how much time each basic operation takes. So in this case, like we can just solve this puzzle, right? So basically you can do it in a logarithmic number of times. So you put 6 coins on one, 6 coins on the other. One of them will be lighter. Then I throw away these 6 coins. Then I take 3 coins on one side, 3 coins on the other side. Now another one will be lighter, so I throw away the heavy one. So then I can do one coin. So this will take like logarithmic number of operations, right? Um, so of course, if we were to code it up on the computer, this won't be a logarithmic time because the weighing is not a constant operation there, right? For doing this weighing, we'll have to sum the sum the weight of all of these entities, all of these coins, and then again sum all of these coins, sum the weight of all of these coins, sum the weight of all of these coins, and then do a comparison. So it's not a constant operation in a computer, but on a different weighing machine, it's a constant operation. So that is why when we're working with the weighing machine, it's order log n. But when we are working, if we were simulating this on a computer, then it would have been would have taken like different amount of time. So we are able to compare ourselves to old algorithms because the basics of computers haven't changed much. Like the arithmetic is still constant time, your comparison is still constant time, and so on. So any questions so far? Anything which was maybe not clear? Yes, Sarthak.
So my doubt was regarding the previous thing, like how do we do a trade-off between number of worst case scenarios and time which we concur for a worst case scenario, like because just a general thought, like if you have two programs and if you have to see which is faster, then would you actually see how many times that program will see its worst case scenario? Because in general, suppose if one program is actually really slow for a few cases, but that probability of having those few cases is really low, then how would you weigh off? Like that was my doubt.
Yeah, so that is a very practical question. That is a very good question. So, so worst case analysis is actually one way to analyze algorithms. So there are other ways to analyze algorithms. So there are ways like average case analysis. So on an average, how does this program behave? Then there are probabilistic analysis. So for 95% of inputs, this program will work well. So depending on where but that goes into where you are using that particular algorithm, right? So depending on your practical use case, you can do a different kind of analysis than worst case analysis. But in general, currently, since we are not thinking about practical use cases of algorithm, we are just sticking with the worst case analysis, because that gives like a very clean clean bound on clean definition of what is worst case and clean analysis. So the thing is, if you go into average case analysis, you can enumerate all the inputs. So that is one way, which is actually the most standard way in algorithm. But other ways can be for your particular use case. What kind of inputs do you see, right? And you can try to come up with average of those inputs and do an average case analysis. But those are like we are not concerned with those in this course.
Okay, sir.
Cool. So yeah, like I hope you can appreciate. Basically, algorithms is and running time is beyond just computers. You can do such analysis and design algorithms for other systems which can have different kind of basic operations. So more recently, this has become very interesting because there has been a rise of a new kind of computers. I think you might have heard in news called quantum computers. So basically, all the hype and interest is because quantum computers support a very different set of basic instructions than classical computers. So because of that, the problem which was really slow or exponential in classical computers can be solved really quickly in quantum computers, right? And vice versa. Some problems are really slow, may really be slow in quantum computers, but they are fast on classical computers. So yeah, so basically the field of algorithm is growing because of that. And okay, there is a comment. Shor's algorithm, yeah. So Shor's is one of the popular quantum computing algorithm. Cool. Okay. Any comments, questions? Okay. Otherwise, let's look at another problem. So basically, let's say we are given this problem, and this is this is a computing problem. So we are given a knight. So okay, let me open a chessboard. So basically, this is a chessboard. So chessboard is a 8x8 grid, and your knight can move like what is called like 2.5 steps. So it can go two in a direction and then one above or below. So two right, one above, one below, two bottom, one right, one then two left, one above, one below, two above, one left, one right. So at any position, knight can have at maximum of 8 different places they can move to, right? So the question is basically we are given a knight position on the chessboard and we are given a king position on the chessboard. So we have to find out in how many ways can the knight reach the king in less than k moves. Right, so a knight is, let's say here is the knight, here is the king. So we have to find out in how many ways can the knight reach king in less than k moves. So maybe let's say k is 3. So let's say it's this position. So they can either go directly or they can go like here, here, and then here. So if k is less than 3, this is also a valid move. Like go to this position, go out of it, and then come back to it. So we have to find all of these number of ways in which knight can move to a given position. So any thoughts like how we can solve this? And or maybe if the question is unclear.
So could you repeat the question? Like how many moves does it?
Yeah, so given a knight position on the chessboard and a king position on the chessboard, find out in how many ways can the knight reach the king in less than k moves, where k is an input, right?
Sir, first we count the number of places from where it can directly reach the king's place, and then we count in how many ways those places can be reached.
Mm-hmm. Yep. Awesome. And do you know what is the time complexity of that approach?
No, sir. I have to think.
Yeah, so think about it and let me know. So basically, this is what is being suggested. So the suggestion is basically, let's say this is the king position. So what I can do is I can just sum up how many I can sum up the number of ways to reach here, 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 or let's say this is the king position. I can just sum up the number of ways to reach here, 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 and here in k minus 1 moves, right? Right. So to reach here in k moves, basically to come here in on the kth move, I'll have to come from one of these positions, right? So I can sum up the number of ways to reach here to reach. So I can sum up the number of ways to reach here in k minus 1 moves plus the number of ways to reach here in k minus 1 moves plus here and so on, right? So that will give me how many ways I can reach this place in k moves. So
Sir,
any
would it be 8 to the power k?
8 to the power k, 8 to the power k. Why power, right? I'm just adding.
Sir, like for every place, there are at max 8 multiple possibilities.
Okay.
So every time it gets multiplied by a factor of 8.
Yeah, so if you write it as a recursive program, I think we saw this in the Fibonacci example. So if we write it as a recursive program, then it is indeed 8 of the power k. So basically this finding the k moves here is a recursion of finding k minus 1 moves here and then adding them up. But as we saw in the Fibonacci example, that is actually pretty wasteful, right? So instead of writing Fibonacci in the recursive way, we can write it in a memoization way, right? So instead of going top down, we can go bottom up and not waste any computation. So basically, that is the approach we will take here. So in this case, let's say our knight is sitting on 0, 0, our king is sitting on 7, 7, and our k is 10. So what we will do is we will create a 3D array of size, size. So this is the chessboard where size is 8, and then of k. So initially, there is no way to, when k is 0, there is no way to go anywhere because k is 0 except where the knight is already standing. So there is only one way. So this is like the base case, right? So there is no way to go to any other location when k is equal to 0 but you can, since the knight is already standing there, there's one way of reaching the same place where the knight is. So then what we can do is basically we increment I from 1 to k and iterate over the chessboard, and we'll say, okay, so the moves is 0 to begin with, and then we'll sum up all the 8 positions where instead of I, we'll sum up I minus 1, right? So this is summing up. So this is calculating in how many ways I can reach this R comma C location in I moves. So this is equal to the sum of in how many ways I can reach R minus 2 C minus 1 in I minus 1 moves plus R plus 2 C minus 1. So these are the 8 moves of the knight. And so but if this position was here, right, we don't want to add this one because it can be out of the range of the chessboard. So that is why we also check whether this thing we are trying to add is inside the range of the chessboard. So in range basically is just a simple function that says your row and column should be greater than equal to 0 and they're less than size. Right. So and then we can print out this number of moves. So let's run this, then we will look at its running time analysis. Okay, so initially when k is equal to 1, because the knight was standing here, the knight can only reach here and here when k equals 1, right? When k equals 2, they can go from this and this position to other positions. So there are 2 ways to come back. So from here and from there. And similarly, so basically from here, it will try to go everywhere, like here, 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 and so on. And similarly from here, it will try to go everywhere. So we get a new number of moves 2D array for k equals 2. And then for k equals 3, 4, and so on, right? So we can see that it quickly, because the growth of number of ways is really exponential, so it is growing very fast. Yeah. Another interesting thing to notice is these are really 0 at so during the this is like, if we call it the odd move. So during the odd move, these ones are 0. And during the even moves, these ones are always 0. And the reason for that is actually pretty intuitive. Like when the knight moves, they always change color. So if I was if I was standing on black, I'll always go on a white square. If I'm standing on white, I'll always go on black square. So in this case, like it's not possible to reach the white square, right? And in this case, it's not possible to reach all the black squares. So yeah, that is the basic idea. So we can go and analyze the running time. But before we do that, is this clear or not at all clear? The algorithm. Hello. Any questions? Okay, I guess I'm hoping it is clear. So the previous student was saying basically this algorithm is 8 power d, and if you write it recursively, that is actually true, but that is, we'll see, is not the case. So let's do this together. So this for loop, what is the time complexity of this for loop? just this for loop.
So size square.
Yeah. Okay. And this for loop, what is the time complexity? Or actually before that, what is the complexity of in range? It's just a constant, right?
Constant.
Okay, so then this for loop, what is the time complexity? So we are doing 3 loops, size, and k.
So k times size square.
Yeah. So it's actually k minus 1, which is the same. So and then rest is just printing, which is this is just printing. So basically this algorithm is order k times size by size, and if you assume size is another constant, if size is just 8, then this is a order k algorithm.
So we do not we don't consider time complexity for printing something.
So printing is generally not considered part of the algorithm, but you could. I mean, because the problem is solved even without printing it.
Oh yeah, yes.
Okay, so that is all I had for today.
Sir,
Yeah,
so can you please explain time complexity again
for this algorithm or in general?
for this algorithm, sir?
Okay, so for to find the time complexity, we basically have to count the number of operations, right? So let's go step by step. For this, so for this loop, how many operations are we making? So we are making just inside the inner loop, we are making one comparison, one increment, and then this one is one assignment, right? So overall, and then this loop is running size times, and the outer loop is also running size times. So the overall time complexity is size times size, right?
Yes, sir.
Yeah. So then similarly for this one, all of this is constant operation. So this is order 1, right? This is just a addition. This is order 1. This is just a addition, right? So overall inside this whole loop is just inside of the innermost loop is just order 1, right? Uh, so the time complexity is basically the total number of times for which we are running the loops. So because there are 3 loops, we are doing k minus 1 times size, right?
Okay, sir.
Yeah.
Thank you, sir.
Mm-hmm.
Sir,
Yeah.
sir, the overall time complexity for this program
Mm-hmm.
should be of order of n square, right?
What is n? N is size.
Size, yes, sir.
Yeah. So it's actually k times size square.
Okay, okay, sir.
Okay. If there are no other questions, um, we can end the session. Cool. Yeah. Thanks everyone. Stay safe.